Welcome to Learn Electrical. In this video we are going to discuss on generation of high voltage AC. The various method of high voltage AC generation I have described in this video. In previous video we discussed on high DC voltage generation, and in this video we are going to discuss on generation of high AC voltage, why high AC voltage is necessary and how are they generated. The general practice of generation of high voltage AC discussed in this video. We all know our transmission and distribution networks are operating on AC. Hence, to test the equipments that are used in power system transmission and distribution, we must have to generate the high voltage AC. Although most of the equipment on the transmission and distribution system are three-phase, we can generate a single phase AC through a single phase transformer that are operating at power frequency, and this is the most common method of high voltage AC testing at power frequency. We generally test the insulators, transformers at power frequency. Similar to low voltage transformation, high voltage AC is generated through a test transformer that have low power rating and high voltage rating. These transformers are mainly used for short time test and high voltage equipment. High voltage test transformer, you can see a test transformer figure of a Torco company. This is a Swedish company which manufactures the high voltage equipments, and you can see the technical specification for this test transformer. And this test transformer usually consists of three windings. The first one is the exciter winding, primary winding we can say, and second one is the high voltage winding. We used to connect the low voltage or voltage that are available at distribution system, that is 220 volt, it is used as primary, and similarly the output that we need is high voltage AC is taken from secondary winding, and the remaining third winding is the coupler winding. If we required much higher voltage AC, then this third winding is used. You can see the three test transformers that are cascaded. For these connections, and the third winding, that is coupler winding, is necessary. This test transformer should have good insulation cells and top and bottom corona free aluminum shielding electrodes. You can see a picture of a test transformer. This is used to generate the high voltage AC in laboratory. As we have discussed, for even higher value of high AC voltage generation, we need these cascaded transformers, and these are the individual test transformer. In this figure you can see three test transformers that are cascaded, because a single test transformer with much higher voltage generation will have larger size and cost, which would be very difficult for handling. So we use this method of cascade transformer to generate higher value of high voltage AC. We will discuss its working and connections in next slide. In this slide you can see there are three winding in this test transformer. The first one is input, and this second winding is divided into two parts, similar for the second test transformer, and for the last one it only have two windings. Just two winding is sufficient to generate the high voltage in cascade transformer for the last test transformer. Okay, this figure is similar to this figure, and ultimately this one is similar to those connections. This is the real figure of the test transformer that are connected in cascade, and these are the electrical connections. I will discuss the electrical connection from this figure. Here in this first transformer you can see a primary winding, a secondary winding, and a tertiary winding. Similar for the second test transformer, and for third test transformer you can see a primary and a secondary winding only, not a tertiary winding. If we need full stage cascading, then it must have tertiary winding so that it is connected to the fourth one. If we give the input voltage V in from the first test transformer, this will induce a voltage V in secondary, and the number of turn in primary of this transformer is similar to the number of turn on the tertiary winding, so that the
input voltage Vin will be induced in this tertiary winding also, which is then connected to the primary of second test transformer, and this will also generate a V voltage, which are connected in series additive connections, so that we are able to get 2 V voltage at this point. And similarly, V in voltage will induce V in voltage at this tertiary winding of second test transformer. This will induce V voltage here, so that we can get 3 V voltage at this point with reference to ground. Hence, if we had just a test transformer which can generate a high voltage AC, that is V, we need to generate the 3 times that high voltage AC, then we need 3 test transformers, and that are to be connected in cascade in this way, so that we can get 3V here. If we further require 4V or 5V, we can cascade these units in similar manner, but generally 3 or 4 test transformers are only cascaded in practice. Okay, here the first test transformer is grounded, and the second test transformer or the tank of the second test transformer would have a voltage of V, and similarly for third test transformer it would have a voltage of 2V, so it should have a proper insulations. So I have shown a difference in height from ground for these two test transformers. All these things are written in this text also, you can read it. The rating for the primary of these test transformers are generally 230 or 400 volt for smaller unit up to 100 kVA or to generate up to 100 kilovolt, and for larger outputs like thousands of kilovolt, the rating of low voltage winding might be about 3.3 kilovolt to 11 kilovolt. Cascade transformers are very expensive apparatus, so it must be protected. We must have a good protection scheme for these test transformers, so it is necessary to limit the high short circuit current by using a limiting reactor in the input stage. Large cascaded transformers are supplied power through a separate motor generator set or by the means of special voltage regulators. These are for cascade transformer. The third method of high voltage AC generation is resonant transformer. In cascading of transformer, we face some difficulties, like the size would be bulky, it would be costly, and the losses are also more, because the losses is the summation of loss of individual transformer, which thereby reduces the efficiency. And whenever we require the high AC voltage with large amount of current or huge amount of current, this resonant transformer method is used. The method name itself signifies what actually it is. It means the transformer will work on resonant conditions. For this, a tuning coil L is needed to make resonance. Hence, the high voltage generation occurs at resonance. Two types of resonance transformer can be made, or generation of high voltage can be made through two types of resonant transformer, that is series resonant transformer and parallel resonant transformer. Here in the figure you can see series, and in this figure you can see parallel resonant transformer. The choke coil which I had mentioned is this in case of series, and this in case of parallel resonance transformer. To understand this phenomenon of resonance, we must understand the resonance phenomenon in RLC circuit, which I have included in the appendix of the slide. Okay, let's revise a little on resonance in series RLC circuit. Resonance occurs in any circuit when the supply voltage and current are in same phase, that is the inductive and capacitive effect of the circuit are cancelled out with each others. In this RLC series circuit, the resonance will occur when this capacitive reactance is equals to inductive reactance, that is XL is equals to XC. At this condition, the circuit will have minimum impedance and maximum current. because we know Z is equals to root under R square plus XL minus XC square. If XL is equals to XC at resonance, then Z equals to R. This is the minimum possible value of Z. Hence, at resonance, impedance is minimum, and for minimum impedance for a supply B, maximum current will flow. This is shown in, this is the curve for current versus frequency. At this frequency, a maximum current will flow, and the frequency corresponding to maximum current is the resonating frequency. Similarly, resonating frequency is given by omega naught is equals to 1 upon root under LC. We also know the quality factor Q can be represented by this formula. Actually, quality factor relates the maximum or peak energy stored in the circuit to the energy dissipated in resistance during each cycle of oscillation. That is, it is the ratio of resonant frequency and bandwidth. Here we will use this expression, which can be derived easily. This expression in our series resonance transformer. Let's discuss more on series resonant transformer. In this figure, the T represents the high voltage test transformer and L represent a choke which can be tuned for resonance, and the C represents the capacitance of the high voltage terminal of pushing of transformer, and the test object, generally this principle or this resonant transformer method is used to test in high voltage cables in dielectric loss measurements, and this C represents the capacitance of the test object. And this series resonant transformer can be made as equivalent circuit, which is shown here. This is the simple equivalent circuit of a transformer, and this L is and C are same from this actual series resonant transformer. Here L1 and L2 are the primary and secondary equivalent winding leakage inductance of transformer. Similarly, R1 and R2 are the equivalent resistance of primary and secondary winding. R0 and L0 represents the resistance and inductance for the core. That is, R0 represents for the core loss. L0 is responsible for magnetization of the core. With this equivalent circuit can be simplified in this circuit, where R is the total or equivalent resistance from this circuit, and L is the equivalent inductance from this circuit, and C is the capacitance. Let B naught is the output voltage across the capacitance C. Now we have to tune the value of L so that resonance occur. As we discussed on series resonance circuit, resonance will occur when the inductive reactance and capacitive reactance are equal. That is, inductive effect and capacitive effect neutralize each other. For a given resonant transformer network, suitable tuning of L will cause resonance, and resonance occurs when XL is equals to XC at resonating frequency FR. Let FR is the resonating frequency. Net equivalent reactive impedance is 0, because reactive impedance, that is XL minus XC, is 0, and so that the circuit behaves as a purely inductive circuit. Thus the impedance of the network will be just R. Let I be the current. If I is the current through the circuit, then the value of current will be P by R. Then output voltage V naught is the voltage across capacitance. So we can say at resonance V out is equals to I into XC. We also know at resonance XL is equals to XC, so we can write XC is equals to XL. So I into XC is equals to I into XL. This is equals to V into XL by R, because I is replaced by V by R from this expression. Okay, similarly we can write V out is equals to V into omega L E by R, that is equals to V into Q, where Q is the quality factor and L is the total equivalent inductance. That is, what we can say is the output voltage is Q times, or the quality factor times the input voltage V. Hence, if a circuit is made with quality factor 45, then the output voltage will be 45 times that of the supply voltage. Hence, a high AC voltage can be generated by this method. And this series resonant transformer principle is utilized in very high voltage generation, and often in the case where high currents are necessary, such as for cable testing, dielectric loss measurement, and partial discharge measurement. For an example, a transformer with 50 to 100 kilovolt voltage rating, or test transformer with 50 to 100 kilovolt voltage rating and a larger current rating is connected together with an additional choke if necessary. It has some advantage also, that is pure sine wave as output, and cascading is also possible. It is simple and compact. It also requires less power because it works on unity power factor. No high power arcing and heavy current surge occurs if the test object fails, because when the test object fails, the resonance will cease. Hence, it will not cause high power arcing. These are some advantages of series resonant transformer. The disadvantage of this series resonant transformer method is we have to withstand the high voltage and high current with the tuning coil also, which is quite difficult and would be costly. This is one of the main drawback of series resonant transformer. Here are some important questions in generation of high AC voltage. Here are two numericals which are similar. These numericals are available in 92 high voltage engineering book. You can refer here. Now the next one is parallel resonant transformer. In parallel resonant transformer, the high voltage reactor is connected as an auto transformer. You can see this high voltage reactor or choke coil L is connected as a auto transformer. The advantage of this resonant circuit is that more stable output voltage can be obtained, and that output voltage would have high rate of rise of voltage and a degree of independency with the tuning, and Q factor can be achieved. Single unit resonant test system are built up to 500 kilovolt. For a single test transformer, about 100 to 200 kilovolt a single unit is made, and for this single unit resonant test system are built for output voltage up to 500 kilovolt, while cascaded units for output up to 3000 kilovolts are also available. Now the generation of high frequency AC voltage. Up to now we are discussing about the power frequency high voltage AC. For the generation of high frequency AC voltage, Tesla coil is used. You might heard about the Tesla coil. In this figure you can see two different coil configuration connected with individual capacitance C1 and C2. The output is taken across the C2. The output waveform is shown in this waveform. For testing electrical apparatus for switching surge, high frequency high voltage damped oscillations are needed, which needs high voltage high frequency transformer. The commonly used high frequency resonant transformer is a Tesla coil. It is a doubly tuned resonant circuit. They have this much for generation of high frequency AC value. This is not in our syllabus. So in this video we discuss about the high voltage AC and its generation. It can be generated through test transformer. If we need higher value of high voltage AC, we can cascade those test transformer and get the higher values. And in resonant transformer we discuss about the operations so that We are now able to understand how resonant transformer works. There are two types of resonant transformer. There are series and parallel. We discuss about that. In the next video, we will discuss on the generation of impulse voltage. These are the reference, the numerical that I have shown. You can get the solution from this reference book. Please refer this book if necessary. Thank you for watching the video.